we have an answer for the derivative?
No.
Still working or just not quite sure?
Not quite sure where to start. Not really sure, but.
So where are you going to start? What would be your first thought? Quotient rule. So our quotient rule is down, D up. So what is the derivative of e to the junk? E to the junk times the derivative of the junk. So that's just 4 x squared, that's just stays the same, times the derivative of the inside, which is x squared, which is 2x. So there is down d up, minus up d down, which is just 2e to the x, all over down, down. And that's when it gets tricky, when you start having like quotient rule and you got to use chain rule inside of it just to keep all that straight of what's going on. Now, so that was the top one. Let's say we have the derivative of this. How can we find dy dx?
That's a good question.
Good thing. So there's what the graph looks like.
Oh, what the actual?
So is that a function? No, it's not a function. But what does the derivative represent in terms of the graph of a function? The slope of the tangent line, slope of the curve, exactly. So we could still do that and say, okay, at this point, what's the slope of the tangent line? We can still find that. Now, here's the tricky part, though. When you find your derivative here, if this was my derivative and I wanted to find what was the slope at x equals 1, what would you do? Take 1 and plug it back in and do all that arithmetic, which we're not going to do. But notice here, this is not a function. So if I want to find at that point, I actually have how many points with the same x? 3. So to find the slope of the tangent line, I'm going to have different answers. So my derivative, dy dx, will have both x's in it and y's, because it depends on the x and the y point. Now, I don't know if it would work on that. These two seem to be similar, right? This one is a completely different sign. So the y down here is going to affect it. So when we find our dy dx for these types of things, our answer is going to have x's and y's in it. Okay? Because what we're finding the derivative are things that are not functions. Okay? Now, before we do a hard one like that, let's start off with some easy ones. So, let's consider this. What is the derivative of x squared? 2x. Good. What is the derivative of sine squared? What's the derivative of sine? Cosine. So this is 2 cosine?
No, it's
2 cosine?
No, just
no. 2 times sine.
2 times sine, derivative of the outside with the inside staying the same, times the derivative of cosine. Chain rule, right? Like I said, that's where it gets hard. We know the words and we say it out loud, but to then not write down 2 cosine is harder. Okay. What about the derivative of 3x squared minus a squared? Chain rule, which would be derivative of the outside. 6x. Now, from what we talked about yesterday, I'm going to add something here. Times 1. So I want you to notice all of these. It is 2 times the inside part times the derivative of the outside. Or derivative of the, it's 2 times the inside times the derivative of the inside, right? So let's say I want to find the derivative of y squared, where y is some function involving x's. Let me show you what that means. Up here, y is sine. Here, y is 3x squared minus a, right? So anything that's squared, where you have some inside part, always is going to have this form. So my derivative will be 2y times whatever the derivative of y is. So here, it was 2 times the inside times the derivative of the inside. 2 times the inside times the derivative of the inside. So this down here is just a general form for all of those ones we've done previously. That make sense?
So it's the same thing as we've been doing.
Yes. But we're doing this based as y is some function. We just don't know what it is. Okay? So let's say we want to take the derivative of cosine of y. Y is some function. Could be anything. We don't know what it is. What would the derivative cosine of y be? What's the inside? Y. So what's the derivative of the outside? Negative sine. The chain rule is derivative of the outside with the inside saying the same times the derivative of the inside, which would be that. And that would be the general form, is if we had cosine of x squared, or if we had cosine of e to the x, or we had cosine of 4x plus 2. All of those, you would use this general form to find the derivative. Does that make sense? So, how this connects to what we talked about before, when we have an implicit equation, do we know what y is equal to? No. So the idea here is we're going to take the derivative like this because we really don't know what y is. But we can still take the derivative because every time you take the derivative of y, it just kicks out a dy dx. So, 2 ways to do this as we go forward with the example. There is the one side. I understand the chain rule. Y is the inside part. So every time I do the chain rule, I have to take the derivative of the outside. The inside stays the same. Times the derivative of the inside. Inside is y, so I have to take the derivative of the inside and get dy dx. Understand what's going on, you're all good. The other side is, I'm not really sure what's going on. I just know every time I do this, I throw a dy dx out there and it works. But I'm not really sure why, but that's how I get the right answer. So what side are you going to fall on? The second one, where you're not really sure what's going on. You just throw the dy dx there, and hopefully it works. So,
I'm on my way though.
so let's look at an example. We have y squared equals x. Simple one. This one we could solve for y, and actually I will in a second solve it for y and show you how you get the same answer either way. Some of the harder ones you can't do both ways. Easier ones we can. So let's look at this. So here's how we're going to do this. We're going to try to find the derivative of y squared equals x. What we're going to do is we're going to take the derivative of both sides. You might not realize this, but if you have an equation, you can add a number to both sides, right? You can square both sides. You can take the square root of both sides. Or you can take the derivative of both sides. That works too. So let's take the derivative of both sides. So what is the derivative of 2y? Or excuse me, I just said the answer. What's the derivative of y squared? 2y times dy dx. Why the dy dx? So you can, because of chain rule, y is the inside, it's explicit, we don't know what y is. Or you could go to the other side and be like, I'm not really sure, you just stick a dy dx there and it works. Whatever side you're on. Now, what's the derivative of x? 1. You're not taking the derivative of a y there, so you don't need the dy dx out there. It's only when you take derivative of a y. So now, if we solve for dy dx, what do we get? 1 over 2y.
That was the easiest part of this.
What?
So, looking at our graph, that would give us the slope of our graph. So, for example, if I was at 1, okay, right here at 1, what's at the x coordinate is 1, my y coordinate is 1. So what is the slope of that tangent line by plugging 1 in there? 1/2. That matches. Now, we also have down here, there, my y coordinate is -1. So if I put -1 in there, I get -1/2. Notice this equation does not have y in it, or excuse me, does not have x in it. It's just a y. So now I can find the slope of the tangent line at any point on this curve, even though that curve is not a function. It doesn't pass a vertical line test. Now, we could get the same thing by actually solving this equation for y. This is one that we could solve. So if I solve this equation for y, I take the square root of both sides, but anytime you take the square root of an equation, you need to deal with plus and minus. So if I solve that, I would get those two equations. Now, from your vast experience taking derivatives, right here, what would dy dx be? What is the derivative of the square root of x? Do we know this one yet? 1/2 x to the -1/2, or I just write it like that.
Or you can do the other way.
Because that's the square root. That would be x to the -1/2, right? So, or you could do that. Either.
Okay.
This is going to be easier when I go to do the next part. So over here, I take the derivative. So what's the derivative over here? Same thing, but I got a negative, right? -1/2 x to the -1/2, which is -1 over 2 square root of x. Is that the same thing we got before? We got 1 over 2y. But notice here, this is why I wrote it the way I did. What is y equal to? Square root of x. So that's 1 over 2y. Over here, what is minus the square root of x equal to? 1 over 2y. So I get the same answer either way. This is with explicit functions. I have them solved for y. That is with implicit functions where they're not solved for y. And you notice I get the exact same answer. All right. Let's do another one.
I think I got this down.
You try. X squared plus y squared is 4. Take the derivative. I'll give you a chance.
Would it be smart to put the y and x on different sides?
Nope.
Okay.
I'm really going with
All right. Derivative of x squared. 2x. Derivative of y squared. 2y. Chain rule, or just do it because it works. What's the derivative of 4? Now, once you get to there, you need to solve for dy dx. So you subtract over 2x, and then you divide by 2y, which gives minus xy.
I just thought the 2's there.
Okay, that works. Now, do you remember what this is a graph of? X squared plus y squared equals 4.
it's a circle.
It's a circle with radius 2. We're conic sections. That's a bad circle, but you get the idea. So you'll notice our tangent line will be the x and y. So if it's up here in the first quadrant, you'll notice x and y are positive, so my slope of my tangent line is negative. If it's in the second quadrant, my x is negative, so negative xy becomes a positive. Down here, they're both negative, so you end up with 3 negatives, so it's negative, and then the same. So you can kind of see how that kind of fits our graph of what's going on. Okay. If you had the same point, think unit circle idea. If you had that point where the x's and y's were all the same, they're just positives and negatives, all that would change is the sign, S-I-G-N, of the slope at all those points. It'd be the same number, whatever that number would happen to be. Now, let's say we wanted the slope of our tangent line at 1 square root of 3, which is close to what I just marked there. How would we actually find that? We'd plug it in, and you would put in there's a math symbol that we will use throughout this year. It's like that vertical line, which basically means
Absolute value half.
I give you credit. That's really creative to come up with it that quick, but that's completely wrong. But I give you a lot of credit for coming up with that quick. I was no idea where he's going, but that was impressive to come up with that. Right. That was short. You came up with it really quick. It was coherent. That made sense, but it was so wrong. But that was good.
Right, so that problem we did with the like was the square root of x on the last problem. That was just to like prove it. Like you don't have to do that every problem.
The both ways?
Yeah.
No.
Oh,
No.
that's what really
No.
threw me off.
No. I was just to show you. I'm going to show you this one both ways in a second also. All right. So all this means, this vertical line here, basically means just substitute in or solve for or evaluate. So all that means is I'm going to plug that point in. So that's minus 1 over the square root of 3. So, and what you could throw that in the calculator or whatever that happens to be. Some number. That would be our slope of our tangent. Now, if we wanted to, we could solve it like this and solve it for y and show that our derivative is the same thing. Let's do this one here. Just, I don't have room on your paper, but if we did, we won't do plus or minus. Let's just do positive. This is a good review of the chain rule. How do you find the derivative of the square root of 4 minus x squared?
Put the 1/2 for 4.
Put the 1/2 in front. Keep this the same. To what exponent? Negative a half. Times, that's the derivative of the outside. Derivative of the inside would be negative 2x. Now let's just simplify here. The 2's cancel. This gives me x over, I still have the negative. This is to the negative 1/2, which means it goes to the bottom and becomes this.
Yeah, me too.
Oh, it's because
1/2 times 2 is 1.
Yeah, that sounds like
get proved by well, you had it, just looks different.
Now, is that what we got in the last one? No, but what was y equal to?
Square root of 4 minus x squared.
So this is just negative x over the y.
Same thing.
Same thing we got before. And we could do the same thing with the negative one if we wanted to show.
I got y.
So now, the first thought may be, well, man, that's a lot easier just to solve for y and do it, and not do the whole implicit differentiation thing. But what happens if we have that? Could you solve that for y?
Yeah. Technically. No, you have to.
No, we can subtract all this over, and you divide. So you could do that. So in that case, you could solve for y. But as we go to harder ones, and I'll go back to where we started today, this one, we cannot solve for y. Okay. So let's finish up with this here today. This is, I'm not even sure, is this on your notes?
Yes.
Go back to the front. Do you have some
No space.
space underneath this one?
There's a little bit of space. There's a good chunk of space.
All right, so let's finish up with this one. We're going to continue with the back, with doing more tomorrow, but let's just finish up with this today. Just kind of do one last example to kind of show you where this is all going, and we'll come back tomorrow and do some more examples. My thought process now is we're not going to have any more homework. You have your 2 chain rule worksheets, right?
Yeah.
We'll continue to do this tomorrow and just do more examples. So we're going to have a project over this stuff also, so you'll know doing this as we go. All right, so derivative of x cubed, 3x squared, plus derivative of y cubed, 3y squared times dy dx. Derivative of negative 2xy. This is technically x. This is the product of x and y. So you have to use product rule. So this is going to be my first. This is going to be the second. So derivative of the first.
Negative 2.
Well, isn't it just...
Okay, good point. So how do you want to, let's talk about that.
Plus 2.
Here's the easier way to do it. Let's do this.
Yeah, that makes
Let's put parentheses there. We'll do minus, and then do in parentheses, so we'll ignore the negative.
sense.
So derivative of the first, 2 times the second, plus 2x times dy dx equals 0 because derivative of 0 is 0. Now what? Now the calculus is over. Now it's just simple algebra. Solve for dy dx. Simple stuff.
Very simple. Alright, so I'm going to subtract 3x squared.
So the first thing I'm going to do is kind of get rid of the parentheses. 3x squared plus 3y squared dy dx minus 2y minus 2x plus 2.
It's minus. Yeah, because you distribute the negative 1. there's.
So now,
Wait,
And distribute.
stop.
Okay.
Question?
why is,
That's all right.
what are you saying? Okay, go back to where you got the 2y plus 2x. Can you do that again?
Please. You don't have to if you don't want to.
Here?
Yes.
Okay, so this is the first.
Yeah.
This is the second. So, product rule. Derivative of the first, 2,
Right.
times the second, y.
Oh, okay.
Plus the first, 2x, times the derivative of the second, which the derivative of y is dy dx.
No, yeah, okay, that makes sense. That makes sense.
Now, here's the quick, easy way to do this. Okay? Anything without a dy dx, move to the other side. Minus 2y goes to the other side, becomes a positive 2y. 3x squared becomes a negative 3x squared. So they are gone from over here. And the only reason I did the 2y first is you could have had negative 3x squared plus 2y, right? Same thing. That's fine.
Doesn't look as good.
Now, the next step. Everything that's left with the dy dx, let's factor out the dy dx. And we're left with 3y squared minus 2x. And the last step is you just take all of that and divide it over, so we get dy dx is 2y minus 3x squared all over 3y squared minus 2x. See, just simple algebra after you do the calculus part.
Yeah.
Getting close to the goal. I didn't understand why.
No, she didn't cry on this part. It was the chain rule part that got her.
This is chain rule.
Where?
This is chain rule.
So,
Damn